Now we see that the constant volatility structure under the Black-Scholes Merton model may not be appropriate. This will make the basically the closed form formula not useful in many situations. Now, if we can, we probably will want to recover that the use of that closed form formula because stuff is simplicity. So in situations where although the volatilities are different, but you can take some sort of an average, and then we can then plug in that average into that closed form formula, and if that works, then we can basically still use the closed form solution from Black-Scholes formula, although we know that the underlying model that we're actually using is something that does not require a constant volatility. So in the situation that you only, if the average is sufficient to describe it, then we can still use Black-Scholes model appropriately. So this is actually similar to what we have seen earlier in the BGM model. So we try to use a simple closed form solution, whereas we're taking, we need the volatility parameter for this model, and then although we know the volatility is actually a function rather than a constant parameter, but in that particular situation that we needed to calculate the swaption, we can use this to calculate a parameter of sigma that we can use for this formula to calculate the price of the swaption. But in many cases, this trick will not work, and we may have to seriously develop alternative models than the Black-Scholes Merton model. So let's take a look at some of the alternative models that we need to construct and look at the pros and cons of these models. So we're gonna talk about basically 5 different type of models. They are, the first one is called the constant elasticity of variance model. The second one is a jump diffusion model. And the third one is a variance gamma model. And then we have a stochastic volatility model. And then the last one is the implied volatility function model. Okay, so let's take a look at the constant elasticity of variance model first. Now, before we launch into looking at those specific models, we basically want to have a sense on when we're going to use those more complicated models. Essentially, for simple options, like a simple European calls and puts and those things, there's very little value to use the more complicated model, because you're going to get it's much more difficult to set up and much more difficult to calculate, and a lot of time you have to do that numerically, and when you do numerical procedures, you will for sure have numerical errors in it. So you go through a whole lot of expense, you may not really get what you are looking for, which is an increase in the precision of the prices. So for those simple options, Black-Scholes is actually very good, or you may be able to just jig the model a little bit by getting some sort of an average volatility, and then you can price it still using the Black-Scholes approach. Now, but for complex options, in particular, certain options that are related to volatilities, then the simple Black-Scholes approach may produce very substantial error or may produce very systematic errors. So in those circumstances, you really have to model the volatility structure much more precisely. Now, the constant elasticity of variance model basically has a form like this here. So the drift part is still the same as the log normal process. Here, the minus Q is only the we're presenting here for a process for a dividend payment stock. So you have the risk-free rate minus the dividend yield. And you should see this is actually a risk neutral process because you have a drift, which is R minus Q. Now, in the volatility here, instead of sigma times S, we have a sigma times S to the power of alpha. Now, in the log normal process, this alpha will by definition equal to 1. And here, alpha can be less than 1 or greater than 1 here. Now, if alpha is less than 1, the volatility would increase when the stock price decreases. Okay, this will produce a heavier left tail and a less heavier right tail. So typically, this will generate this the volatility skewness that we typically observed in the equity market. So if S is a stock price, and typically in modeling, people will restrict this alpha to be less than 1. On the other hand, if alpha is greater than 1, then you will have a thicker right tail and a less heavy left tail. But that's not typically observed in the market. So if you're modeling the stock market and you worry about changing volatility, and one way to generate that skewness is to have a constant elasticity of variance model with a estimated alpha value that you force it to be less than 1. So this model here cannot really be used for the currency market. So you can't really use this model if S is the exchange rate, because this doesn't generate this smile. So this model will only generate skewness and would not be able to generate smile. Okay. So this basically gives a graphical representation of that. So you have a volatility skewness here, which is something typically observed in the equity market. You can somehow, you need to determine what actually the alpha parameter is. Now, one nice thing about the CEV model, or the constant volatility, constant elasticity of variance model, is that they do have closed form solutions. So in this case, if alpha is somewhere between 0 and 1, a simple option will have this pricing formula here. So here, instead of compared to the Black-Scholes-Merton formulation, instead of using a cumulative normal, you need to use a chi-square distribution here. Now, as I mentioned earlier, you're not really going to use a model like this to price the simple option. But if you have the the closed form solution here, however, you can use the price observed from the market to calculate some of the implied parameters. Like for example, in this case, the key parameter you need to know is what is the actual alpha value. You know it's greater than 0, less than 1, but what exactly that value is. So you can use the observed simple option prices like calls and puts, and utilize this closed form solution so that you are able to back out what the alpha term is and what the volatility term is. And then once you are once you have those parameters, the volatility and alpha, then you can directly use this process, and you can use numerical routines to calculate more complex derivatives, but that are following that with the underlying stock actually following this particular process, where you get the sigma value and alpha value from the observed market, okay, from the observed option price, simple option prices, the option prices of prices of simple options, okay. So sometimes in many cases, when you have a whole set of calls and puts, in order to recover alpha and sigma, you can't just determine one first and then determine the other. Most of the times you will have to determine both of them simultaneously through some sort of a numerical optimization scheme.